الآن. أحمد نبدي؟
اي نعم، اي واضح صوت. تفضل دكتور.
نعم. بسم الله الرحمن الرحيم. مساء الخير جميعا على جميع الحضور. في البداية أحب أشكر عمادة كلية الهندسة جامعة القادسية متمثلة بالدكتور علاء لايق ورئاسة قسم الهندسة الميكانيكية لإتاحتهم هذه الفرصة للتحدث عن أحد البحوث اللي نعمل عليها حاليا في جامعة اوكلاهوما ستيت يونيفرسيتي. في البداية أحب أعرفكم بنفسي. قسم من حضراتكم يعرفني، الآخر لا. اسمي أنا دكتور علي فاهم. This is my background education. Currently, I have a postdoc with Professor Rامن in Oklahoma State University, and I finished my PhD in the University of South Carolina, 2019. My master in aerospace structure and mechanical engineering in 2017. I have already another master from University of Baghdad in applied mechanical engineering, and my bachelor's from same University of Baghdad in Iraq. This picture we just took it last January 2020. You can see from the left there is a 3 PhD student, Farin, and Place and Achu. These are PhD students in our lab. Professor Rامن in the middle, I'm in the left. So this is just a brief introduction. Now, our speaker today. Our speaker today is Professor Rامن. I will start his background education. Professor Rامن joined Oklahoma State University in 2006 as an assistant professor. He finished his postdoctoral scholar at California Institution of Technology. His PhD in mechanical engineering and applied mechanics from University of Rhode Island, 1995, and he have mechanical engineering and applied from the same university. Professor Rامن he work حاليا هو مساعد العميد في كلية الهندسة وأستاذ ورئيس قسم في قسم هندسة المواد في الجامعة نفسها. أيضا أستاذ في قسم هندسة الميكانيك والطائرات، ومدير لمركز بحثي في مدينة تولسا، ولهذا اسم الجامعة أوكلاهوما ستيت يونيفرسيتي and Tulsa is the name of the campus. المركز البحثي يضم مختبرات عديدة ويعمل على تطوير they call it large volume applications. الكثير من البحوث المتقدمة. اليوم راح نتحدث عن واحد منهم. Major area of research for Professor Singh, filler mechanics of advanced and complex material system, and his background work on experimental mechanics, fracture mechanics, composite materials, dynamic failure, large volume applications, basically dynamics behavior of material with high loading rate or intermediate loading rate. He has funded his research funded from different resources, NSF, National Science Foundation, NASA, Oklahoma Center of Advancement, also United States Army Research Office. Professor Rامن, who active members in Social or Society of Experimental Mechanics and American Society of Mechanical Engineering. So far, he has more than 100 papers published in journals and more than 2,000 citations. So this is just the outline. Maybe he can tell you more. Today, Professor Rامن is going to talk about using of AFM-based nano-identification to quantify mechanical properties of fiber, matrix, and trace. Basically, or in simple word, حاليا الصناعة بدأت أكو نظرة للنقلة الصناعية جديدة، تحول من استخدام البطاريات إلى استخدام هياكل المكان أو يعني مثل السيارات تستخدم البطاريات حاليا، لكن اكو بحوث حاليا لاستخدام هيكل السياره او هيكل الطائره لخزن الطاقه الكهربائيه واستخدامها دون الحاجه لاستخدام اي بطاريات اضافيه. طبعا هذه اكو ادفانتج اللي راح يقلل الاوزان ويقلل الخطوره نتيجه مبدا عمل البطاريه تعتمد على التفاعلات الكيميائيه. البحث هذا هو عباره عن شطرين، الشطر الاول يختص بتحديد الخصائص الميكانيكيه وتطويرها، والشق الثاني يعتمد على تحسين المواصفات الكهربائيه باستخدام الفايبرز والكربونز والنانو تكنولوجي. اليوم راح يتحدث البروفيسور عن موضوع الخصائص الميكانيكيه وتطويرها. الموضوع الخاص بالجزء الكهربائي احتمال تكون عندنا ندوه ثانيه لعرض التجارب والنتائج بعد نشرها ان شاء الله في المجلات. Up to this point, I'm done. Now, Professor Raamen, your time, and thank you.
Thank you, Ali. Thank you for coordinating and organizing this, and thank you for keeping me focused in terms of doing this. I hope you can all hear me clearly. Unfortunately, I don't speak Arabic at all. Maybe one or two words here and there. I can say shukran and things like that, but other than that, so you will have to listen to this talk in English. I'm going to share my screen, and if there are, feel free to ask questions throughout the presentation. You can type them in the comments if you need to, and I will respond to them. Otherwise, we can wait till the end and then discuss. I have about 30 slides, so I'll talk for about 40-45 minutes, and I'll take my time and kind of give you a little bit of background of who I am, the kind of research I do, and then focus mainly on one aspect of one of the research projects we focus on. So I'm going to go ahead and share my screen. Okay, I hope you can see all this clearly. If I need to zoom in, I can zoom in. Let's go. All right.
Yeah, it's clear.
Yeah, so like Ali said, that I am Raamen Singh. I'm the Associate Dean for Engineering at OSU Tulsa, and I have a very strange mix of both administrative and research titles, and this is because the main Oklahoma State campus is in Stillwater, and Tulsa is a side location, and I handle things in Tulsa. My background is in mechanical engineering. So my original degrees are in mechanical engineering and applied mechanics. And I head the School of Material Science right now. And most of my research actually involves both mechanics and a lot of materials work as of late. This talk that I will give is primarily mechanics focused. So the idea is that we want to use atomic force microscopy. So we want to use atomic force microscopy based nanoindentation in order to get the mechanical properties. And the reason for doing this and why we are interested in understanding the fiber matrix interface, I'll walk through all of that. So I work at the Helmrich Research Center. This is a photograph of the Helmrich Research Center. So the idea is that this is a material science focused center that sits in Tulsa. And the main campus is in Stillwater, about 100 kilometers from where we are in Tulsa. But the idea is that even though we have two separate locations, it's the same college and comes under the same environment and everything else. So this building over here is the building in which Ali works. This is where, my lab is. And when I started working at Oklahoma, I started basically working in this building. So I am originally from India. So I grew up in Agra, which is the first city I grew up in, where you have the Taj Mahal. So it's one of the 7 or 8 wonders of the world. And I came to the United States. And when I came to the United States, I originally came on the East Coast. So if you look over here, that's where I came. That's where I did my PhD. And I finished my PhD in '95. And then I went to the West Coast, where I did my postdoc. I was there for 3 years. And then after 3 years, I went again back to the East Coast to start as a faculty member in SUNY Stony Brook. So I had gone back and forth 2-3 times. In 2006, I was looking to move. I was looking for a position to move. and I saw a position advertised in Oklahoma. So if you don't know where Oklahoma is, it's basically pretty much in the center of the country. It is north of Texas, and it's not many people come to Oklahoma when, unless they have a reason to come to Oklahoma. So you don't go to Oklahoma because of anything else. So when I was looking for a position in 2006, there were two friends of mine that I had known from my years in Caltech who were faculty members in Oklahoma. And one of them was actually serving on the search committee. So when I asked them about the position, it was focused on composites. I had been doing a lot of work in composites at that time, and they said it's in Tulsa. And so 2006, I moved here with my family. My two daughters were just starting to go to school. And so I have been here for 15 years, and I've been very happy. It has turned out very well. And it's interesting that personally also, so both my daughters now are done with the high school. The older one is in college, and the younger one will start college soon. So big part of my life has been spent over here. I have lived in a lot of places. So when I grew up in India, I lived in various parts of India. And then, when I came to the US, I lived in various parts. And so these are, I've lived in several cities all my life. And this is a picture of me. This picture is probably 92 or 93 when I was a graduate student. So a lot of people don't believe that I had hair then, but I actually had hair then. And I still have the mustache. So this is doing dynamic experiments. And Ali will be interested to know that this is actually a high-speed camera. This is a spark gap high-speed camera we used to have in those days, and the whole thing ran on very powerful capacitors, and it ran on high voltages, and obviously it was not portable, and now we have digital high-speed cameras. So my original area of interest started in looking at dynamic behavior of materials, but then I didn't do dynamic behavior of materials, and I switched, and these are the areas that I work on. And some of these areas are very active, and some of these areas are not as active. My group right now is a little bit small. I have Ali in the group, and I have 3 PhD students, and that's because I have a lot of because primarily my role is administrative. So managing a large research group is not easy. But we'll probably grow to about 8 students within a year, and then I want to keep it constant. So I would say I have spent about 20 years looking at the behavior of composites and understanding their long-term performance. So that's the first bullet point you look at over here. And because we needed to understand the long-term performance of composites, we got interested in looking at the fiber matrix interface. And that basically led us down the line in terms of developing these nanoscale mechanical property measurement tools. So I'll talk about that. There are other projects in here that are relatively newer for us that I won't talk about right now. We do a lot of work with functionalizing fiber matrix interfaces using polymer chemistry and tuning those interfaces. I have done some work in the past in polymer-derived ceramics and ceramic composites. This is not active right now, but I'm trying to collaborate with the faculty member to work on this. And recently, we have been doing a lot of work in looking at dynamic failure of shale. So dynamic failure of shale is what, and this is the project that Ali came on board, and we have a couple of people working in this area. So for today's talk, all I'll focus on primarily is our focus on looking at the long-term performance of multifunctional composites and how we are using nanoscale property measurements to try and answer this. Okay. So why are we interested in multifunctional composites? So multifunctional composites we are interested in terms of taking the same composite material that you have. So let's say you have a composite material that is used to make an aircraft wing, or it is used to make a car body panel. We want to provide multifunctionality to that. So multifunctionality means that it will not only take the load-bearing applications, but it will do other things. For example, you can use these panels to store electrical energy. That's using car body panels to serve as a battery. And this is an automotive body panel that Volvo had developed for some time. It never got commercialized. The idea is to store electrical energy above aircraft. So then you can have other multifunctionalities. For example, you can design composites so that they can protect from lightning strike. The idea is to take one material and modify it so that it can do more than one function at the same time. So when you take the same material and you modify it so that it does more functions at the same time, its performance also is now subjected to these multiple environments. So this is a very involved problem. So if you're looking at and we'll focus only a small part of this and focus about that. So if you're looking at the performance of multifunctional composites, the first question is, how do you define performance? So if I have a composite that only is used to support load, then all I need to talk about is failure modes, residual strength, durability. But now when it has other capabilities, then I have to talk about multifunctionality. For example, what will be the thermal characteristics? What will be the electrical characteristics? Related with this performance is the operating environment. So the operating environment can be mechanical, it can be chemical, it can be environmental, or it can even be multiphysical. For example, you can talk about having electrical conduction in composites that are designed to store electrical energy, or composite materials that are designed for lightning strike protection. And this thing basically leads to the idea of degradation. So as you use this material over a long period of time, you'll get degradation, and we are interested in different aspects of degradation. And because you have to try and understand these multiple aspects, you require unique tools also. And so for the rest of my talk, basically, I will start talking about multiple environments operating at the same time, and then relate that to the use of basically unique tools, and look at characterization at very small length scales of the fiber matrix interface. So we got interested in this problem a long time back. This is work that was published when I was at SUNY Stony Brook, and a couple of graduate students worked on this. If you take a composite laminate, so a composite laminate is basically layers of the composite, and in each layer you have fibers in different orientations. So you can make what is known as a 0-degree laminate. So this, for example, would be data for a 0-degree laminate over here. You can make a 90-degree laminate, and you can make cross-ply laminates in which you have both 0 and 90 degrees, right? So you take this composite and you subject it to a certain environment. And when you subject it to a certain environment, the easiest thing to monitor is to see how the weight changes. So I will walk you through this. These are experiments from 3 different conditions. So the first condition that we look at is here on the left. So you look at this condition of the left. Here what we are doing is we are taking these composite laminates and we are subjecting them to UV radiation. Why is UV radiation important? Because these composites are used outside in the environment, and you have UV radiation from the sun, or they can be used in space applications, and there you have cosmic radiation. So you have ionizing radiation that causes damage. So you take a composite laminate and subject it to ionizing radiation, you don't get any weight change. I mean, the weight remains about the same because you're not doing anything physical. You may be causing some cracking, some micro cracking and things like that, but you're not adding anything to the material system or removing it. When we look at aerospace applications, we worry about 2 environments. So we worry about UV, and we worry about condensation or the presence of moisture. So if for example, I have, let's say, an aircraft structure, an aerospace structure, that goes from Florida in the United States, which has very high relative humidity, to let's go to Iraq in the summer, right? And Iraq is very low relative humidity. So it is subjected to this big change in the relative humidity. So if we take the same composite and expose it to condensation, what we see is that we see an increase in weight as a function of time. So this is weight over here, plotted as a function of exposure duration. So we see an increase in absorption of moisture in the composite, and this can be explained by simple analytical models. Now, if I combine these two environments and I do UV radiation and condensation, and I do it in a cyclic manner, if it was a simple superposition, you expect that the weight change that you expect will be a sum of this and a sum of this. But instead, when you carry out these experiments, so if we carry out the exposure of UV radiation and condensation in a cyclic manner, then we observe that the weight starts decreasing after some time and continues to decrease. So the reason I talk about this is the first time that anybody had looked at two environments operating on composites to see what would be the long-term effects of that. And we were very surprised when we saw this. And what we found was that if you have both these environments working at the same time, you actually cause physical damage to the composites. And this is a work that first got us started into looking at synergistic degradation mechanisms, and it was published in 2002. So this is a historical paper for our group. These are two images from composite laminates, and what you can see is that we are losing the epoxy. So these are the carbon fibers that you see. These are carbon fibers coming out of the plane of the screen, and if you look over here, you see carbon fibers running across the screen. So this would, on the top, you would have one layer. This is a 90-degree layer over here. Then you'll have another 0-degree layer. And if you zoom out a little bit, then you see the thing on the right. It's the same thing. So what we found was that when both these environments act at the same time, we actually get physical removal of the epoxy. And when you get this physical removal of the epoxy, you start degrading the fiber matrix interface. And if you start degrading the fiber matrix interface, now you don't have a mechanism for transferring the loads from the matrix to the fibers. So if you're familiar with composites, the way composites work is that you have these carbon fibers. If you have a carbon fiber composite, you have these carbon fibers inside the matrix. And when you load it, there is load transfer that occurs from the matrix to the fibers. And the fibers take the load, but the matrix has to provide this load transfer. And this load transfer goes through this fiber matrix connection. So that connection is very important, and how that connection changes if you expose it to different environments becomes very important. So the picture we are seeing over here and the picture we saw over here, these are very macroscopic pictures. I mean, they tell you what is going on in a very large scale, but they don't actually get into the fundamental mechanisms of what is going on at the fiber matrix interface, and that is what we were interested in. This breakdown affects everything. This primarily affects things like fatigue. So if I take the composite laminate that has been subjected to degradation and I subject it to fatigue, the fatigue life is much less than what it would be otherwise. We did quite a few experiments, and primarily in terms of understanding fatigue, and also in trying to understand if I had loading, how that would end up affecting the degradation process. And we found that that depending on how I was loading the composites was also affecting the degradation process, right? So this is the background which basically gets us to today. So what I have now is that I have the carbon fiber and I have a matrix. And I want to try and understand, if I take this system and subject it to an environment, then how does that environment degrade the system so that you affect the load transfer between the matrix and the fibers. Whatever we saw till now, the changes in the fatigue characteristics, the change in mass and all of that, that happens much later. First, you will start affecting the properties that you'll start affecting. The initial effects will be very small, but if you can start identifying the initial effects, then we can try and understand, what's going on at the fiber matrix interface. So if you take a cross section, this is what we are looking at over here. So if you take a cross section, you have the carbon fiber in the center, which is about 5 microns in diameter, and it's embedded in a matrix. And there is some region between the fiber and the matrix, which we call the interface, which is basically the matrix material, but its properties have changed because of the curing process. And for carbon fibers, it is speculated that this layer of the interface is somewhere between 10 and 50 nanometers. That was the speculation. But this interface is now responsible for the load transfer from the matrix to the fiber. So we want to try and understand this matrix, the properties of this interface. Not only do we want to try and understand the mechanical properties of this interface, we also want to try and understand what happens to the changes in this mechanical property if I take this composite and subject it to some kind of environmental degradation, right? Carrying out mechanical tests at a length of 50 nanometers is very difficult. You can do indentation, but you cannot do regular indentation. You have to do indentation using an AFM. So this is an atomic force microscope that we have in the lab. The actual microscope is inside this box over here. And even inside the box, you will see that there's a lot of vibration isolation and positioning systems, and the AFM is over here. If you're familiar with AFMs, then you will know this, but if you're not, they work on a very simple principle. There's a cantilever beam, and at the tip of the cantilever beam, there's a micro machined silicon tip, and the tip basically interacts with the surface. And the way AFMs are typically used is you try and map the topography of the surface. You can map the topography of the surface, you can map the chemical characteristics of the surface. What we want to do is we want to take this tip and we want to drive it into the material and carry out an indentation experiment at the length scale of an AFM tip. And if we can do that, then we can analyze the indentation data to basically get what we're doing. So several people studied the interface region in carbon fiber composites. The primary work is by Larry Drizal, who is at the University of Michigan. He's still active. And recently in 2014, there were a couple of papers that came out that started using AFM force mapping, which is the technique we use to start looking at this interface properties. But till now, till we started our work, no studies had focused on the degradation of the interface region. So not only do we want to study the properties of the interface region, we also want to study how these properties change if you take a composite and subject it to an environment. Okay. The specimen preparation is very challenging. On the left, you see an image which was cut through with a cryomicrotome, and you can see that the interface is damaged. On the right side, we see a mechanically polished specimen surface. So when we do AFM mapping, we have to make sure that we are polishing these. Cryomicrotoming doesn't work, mechanical polishing works. And these are the carbon fibers you're looking at. So these are the 5-micron carbon fibers. This is the epoxy. And we carry out all of our experiments in a tiny, tiny, tiny region right next to where the fiber sits and the matrix sits. That's where all of our measurements are made. So this gives you an idea of what sample preparation looks like. So you want the height of the region that you're looking at to be much smaller than the depth of indentation. So if we look at, so this is a carbon fiber, for example, and we are looking at a 3D mapping over here. This is the carbon fiber. This is the epoxy matrix. If we pick this tiny area in here, we look at this image to the right, then I see in a region of a micron by micron, approximately. So a micron by micron, approximately, the maximum height variation I have is from -8 to 8 nanometers. So this is relatively flat. That means I can carry out my measurements with indentation over here. So this is what the indentation experiments looks like. And I will explain this to you because this captures all the experiments we are doing. So what you're looking at is you're looking at a region in the carbon fiber epoxy matrix cross section, which is about a micron by micron. And so 870 nanometers by 870 nanometers. And this is about 960 nanometers versus 960 nanometers. And this is split into a grid of 48 by 48. So I have 48 divisions this way and 48 divisions this way. So each one of these squares is one of those divisions. The region we are looking at basically is we are focused right at the carbon fiber matrix interface at one of these regions. This dark red area that you see in the bottom corner, this is part of the carbon fiber. This region that you see, the blue-green region, this is the epoxy matrix. And between this region, you have a tiny layer, which is not the carbon fiber, which is the epoxy region, which has properties different than the bulk part of the epoxy region. So what we do is, in our AFM force mapping, is we go to each and every one of these points. So we have 48 by 48. So all of these points, we go to each and every one of these points and carry out an indentation experiment in which we load, we measure the displacement, and then we unload and we measure the displacement. And then we go to the next point, we do loading and unloading. We go to the next point, we do loading and unloading. So on each one of these points, I can determine the indentation response. And if I know the indentation response, then I can do several things. For example, I can calculate the modulus. So I know the modulus at each one of these points. And what I observe is, if I come from the bulk epoxy close to the carbon fiber, there is an increase in the modulus that we get over here. And we look at this data, I mean, quantitatively rather than just, in different images. One of the things that we do is that we use the adhesion map, which is also generated during these indentation experiments, to figure out exactly where the carbon fiber lies. So this is the same image. You're looking at the adhesion map. So the adhesion with carbon is very low. Adhesion with polymer is very high. So you can figure out exactly where the carbon fiber interface lies, right? And each one of these points represents a data set. So these are load versus displacement curves that we get from each one of those data sets. So I can go over here, and from each one of these data sets, I can pull out a load versus unloading curve. So that is the amount of data that is represented. If I can do it for every point, then I can do it as a function of distance from the fiber, the distance from the fiber. So I start plotting load displacement as a function of how far from the fiber I am. So if you see this black solid line over here, the last one, this is 600 nanometers away from the fiber. And then I keep coming close, 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 and then the green one is basically right on the fiber, and then these ones are right in the interface region. So I can get these load displacement curves. From these load displacement curves, I can get different things. For example, I can look at maximum indentation depth and so forth, and I can get the modulus. But right now, you know that if you look at this black curve, the black curve is much less stiff than the curves that are closer to the fiber. So what I'm seeing over here is, I have my carbon fiber. I carry out my indentation. If I'm far from the carbon fiber, then the indentation response is very soft. If I'm right next to the carbon fiber, then the indentation response is very stiff. That means that this region over here, my interface region, has a modulus that is higher than the rest of the bulk epoxy. So this is very interesting, because this is one of the first measurements which shows that the interface region has a higher modulus. How much higher? Let's try and figure that thing out right now. In an indentation experiment, regular nano indentation experiment, I take the load displacement curve and I analyze it using analytical data. And basically I look at the unloading curve, and from the unloading curve, I can get what the modulus is. But I need analytical equations. So we have the solution, elastic solution of an indentation on a semi-infinite half space. We've always had this. This is how I analyze my regular indentation data. Unfortunately, the problem we have over here is that I am carrying out indentation right next to a fiber. The elastic modulus of a carbon fiber is about 3000 GPa or 300 GPa. The elastic modulus of a matrix is about 3 GPa. So the fiber is 2 orders of magnitude higher stiffness than the matrix. So as far as the matrix is concerned, this is rigid. The fiber is not going to go anywhere. So now, if I was to carry out this indentation is affected by the presence of the fiber because you have constraint. So if you know elasticity solutions, then you know if I have a constraint, I'm not allowing this part of the matrix to move, then the indentation that I will get will be different if I was doing indentation when there was no constraint. So for a from a elasticity viewpoint, the question is as I get closer to the interface, is this getting stiffer because I am seeing a different material property, or is it getting stiffer because I am seeing constraint because of the fiber? And this has never been addressed until the work we did, because there are no analytical solutions to this. So because there are no analytical solutions to this, there are some finite element solutions. So we started with the finite element solution of looking at the elastic modulus divided by the unconstrained elastic modulus as a function of distance from the fiber. So as I come closer and closer and closer to the fiber, my modulus goes up. These FEM data, these FEM solutions assume that the material doesn't change. So the increase in modulus that you get is only because of the constraint effect. And this is how the indentation process looks. And we have modeled both 2D and 3D indentation, and we have also compared ourselves with results in the past. So that tells us what's going on. But now we know that the constraint effect is real.
Can I ask a question, Professor?
Yes, Ali.
Can you go back to one slide, please? One more?
Yeah.
Yes, here. If you look for elastic properties, when I follow the black line, you see that suppose I have one path. I see now when you're loading and unloading, the path is different. So that means there is some plastic deformation when you go farther from the fiber, something like this.
Yeah. So this is a good point. So what you see is that there is the loading path here is different than the unloading path. That means you see some plastic deformation. So that is why we use the unloading, because the unloading will be only elastic, right? So we use the unloading part to get elastic properties. If I'm interested in elastic properties, there's one more thing that happens which doesn't happen in regular indentation, is that when I unload, I will see that my load goes negative, because now as I'm pulling the tip out, there is some adhesion that is happening. So the polymer sticks, the polymer doesn't want to let go. So that's why we get some negative loads over here. This is the adhesion effect. So this is the adhesion effect, and the difference over here is the difference between elastoplastic deformation and purely elastic deformation. But as a first step, we are only interested in the elastic properties. We can actually analyze these to get viscoelastic properties also, and we have done that, but I won't talk about that today. Right? But all that analysis requires us to have a solution for this, which we don't have, right? So if we look at, and this is just to point out what we are looking at. So if we look at theoretically, if I was to do indentation, unloading, loading in an elastoplastic region, basically what I see is that this is load as a function of displacement, and I see that as I keep going further and further away from the fiber, this is a finite element result, my depth of indentation keeps increasing. Right? But the unloading part, the curve doesn't change until I start coming very close to the fiber. That means the constraint effect is not kicking in until I'm very close to the fiber. So if I look at the slope of the unloading curve, this is from finite elements. So if I look at the slope of the unloading curve over here, unloading curve, they're all the same. That means, and that makes sense, because you have the same material, but you don't have any constraint effects. You start seeing constraint effects only when you start coming very close to the fiber. So we took the finite element work and we took our experimental work and combined both of them, and this is the combined result, and this basically explains to us what is going on. So backtrack before we get lost completely. I have a carbon fiber, I have an epoxy matrix, I have an interface between the carbon fiber and the epoxy matrix. I carry out an indentation experiment which tells me the elastic modulus. I don't know if the elastic modulus is going up because of the constraint effect or because the properties themselves are changing. So I carry out a finite element simulation in which I can look at this ratio, E divided by E unconstrained, and I get this line on the bottom. So all of these lines on the bottom, the last 4 data sets over here are from finite elements 2D or 3D. And this red line is a fit to the experimental data that we get. So what we find is that there is a constraint effect. Yes, there is a constraint effect, but the constraint effect does not come into play until I'm very close to the fiber. So this x-axis is the distance from the fiber. And the constraint effect is much smaller than the experimentally observed increase in elastic modulus. So we are actually seeing an increase in elastic modulus in the interface region. The width of the interface is about 150 nanometers. And the amount of increase that you see in the elastic modulus is at least 3 or 4 times the rest of the matrix. Now the problem is that if you're seeing this, this means what? This means that the epoxy, the way these composites are made is that the fiber, and then you put the epoxy and you cure the epoxy. The only reason why this is higher is because the curing characteristics of the epoxy right next to the fiber are different. And now that has changed. The probably cross-link densities are higher because of the presence of the surface, and that's why the modulus has gone up. So this modulus will then end up affecting the load transfer mechanisms. The second question now we ask is, now that we have this interface, how will this interface be affected by an environment such as UV degradation? So an UV degradation of polymers has been well studied. So if I take a pristine polymer and I take and expose it to UV radiation, this is what I get. So they are both, again, this is AFM data. They both are exposed to exactly the same conditions. And both these 2D plots are on the same color scale. So you can see that you go from a modulus which is closer to 4 or 5 to a modulus 3 or 4 to a modulus which is closer to 2. So you see a decrease in the elastic modulus if you take a polymer and expose it to UV. Makes perfect sense. If I take a carbon fiber and look at the interface region and I expose it to UV, what we see is, and these are not the same material, these are different materials, because you can't basically take the same specimen and expose it, but they show the same thing. So here I have the carbon fiber, here I have the matrix, here I have a well-defined interface, and if I take a specimen which has been exposed to UV, I find that the modulus here has now gone up, and the interface is not as clear as the interface earlier. When we look at models of UV, the effect of UV on polymers, there are 2 models that come into play. Before I go there, I'll talk about this. There are 2 models that come into play. One model is UV is ionizing radiation, so the energy that you put breaks up the chains. You get something which is known as chain scission. If chain scission happens, chains break up, then the modulus goes down. But ionizing radiation can also cause increased cross-linking. And there's usually a question of what happens. Do you get chain scission? Do you get cross-linking? And our other question is that how does the presence of carbon, so the carbon sometimes can catalyze this process. So if carbon catalyzes this process, then you will get even an enhanced amount of UV radiation. So what you're looking at over here is a lot of information. So I'll just slowly walk you through it. These are multiple experiments done at the carbon fiber matrix interface for different levels of UV exposure. So no UV exposure is what we looked at earlier. Then after 30 minutes, 1 hour, 2 hours, 6 hours. We are plotting elastic modulus as a function of how far we are from the fiber. So if you look at if you can follow with me, and if you look at the blue curve, what you see is that this is the blue line. So this is the elastic modulus, and it is it's about 3 GPa when you're far from the fiber. You come to the interface region and the elastic modulus starts going up. Now, if I expose the same material to more and more UV, what I find over here is that the elastic modulus changes. First, it appears to decrease, and then it appears to increase depending on the exposure duration. And I get a similar trend over here that first it tends to decrease and then it tends to increase. So I can pick a certain point and look at the elastic modulus. So this is the same data that we are looking at, but we are looking at it slightly differently. So I'm looking at the elastic modulus as a function of duration at various locations on the sample. So this is the variation of the elastic modulus at 20 nanometers. As I expose that point to UV radiation, and the blue line over here is what I would get if I just took pure epoxy. The green line over here is the behavior of the polymer at 600 nanometers, and the red and the black lines are closer to the interface region. If you start with the blue line first, this is what we get. I take an epoxy sample, no carbon fiber, no interface region. I expose it to UV, and there is a slight decrease in elastic modulus as time goes on. Chain scission, we understand exactly what is going on. If I take carbon fiber, if I take bulk polymer that is in a composite, so I'm sitting at 600 nanometers, this is where I'm sitting. Initial behavior is the same as what I expect in the case of bulk polymer, but then what I find is that after about 1 hour, the behavior of the bulk polymer region in the presence of a carbon fiber composite is different than if it was just purely a polymer, because the UV radiation of the carbon fiber produces these free radicals that then diffuse through the polymer, and the further you get, the further you get, the slower they diffuse, and as they diffuse, they produce increased cross-linking, which is not seen in the bulk polymer. The effect of cross-linking is more and more pronounced the closer and closer you are to the carbon fiber interface. So the 40 nanometer region sees increased cross-linking very early on. The 20 nanometer region sees increased cross-linking very early on. So the increase that you see over here is due to the effect of the carbon fiber presence, and then the time decay happens, and as you keep going further and further down in time, you start seeing chain scission happening. So this is a snapshot of the degradation of a polymer in the presence of a carbon fiber as a function of time as you go further and further away from the carbon fiber. So we find that the presence of the carbon fiber ends up affecting not only your starting modulus, so this at time t equal to 0 is your starting modulus, but it also ends up affecting exactly how this modulus changes as a function of time. So in order to understand degradation in these materials, not only do you have to know that the presence of the carbon fiber is affecting the degradation of the material when we expose it to UV, but it is also affecting it depending on how far or how close we are. Okay? So this kind of summarizes the status of this work right now. So we are one of the first people to look and characterize the interface properties in carbon fiber reinforced epoxy using AFM nanoindentation. What we find is that the width of the interface is about 250 nanometers. We find that there is a constraint effect. The constraint effect affects the indentation data at 20 nanometers and 40 nanometers, but once you are outside this region, the constraint effect does not affect the nano indentation data. And then what we end up seeing, an increase in 2 to 3 times the modulus, is actually the changes in the properties of the interface region. When we look at UV degradation, we find that UV degradation in the near fiber region is very different than the bulk behavior. And the further you are from the carbon fiber, the autocatalytic effect that happens because of UV degradation from the carbon fiber is different, right? Where do we go next from here? It would be nice to be able to fit autocatalytic kinetic mechanisms to this, because this is data that is observed at very small length scales and very short time scales, and then figure out if we can actually predict the autocatalytic effect of the carbon fiber on the UV degradation behavior. So this brings me back to the end of my talk. I don't know how good we are doing. Okay on time, and we continue to use the AFM indentation experiments for different things that we are doing. But this work is kind of stopped because the person who was working on this graduated. So until another PhD student comes on this work will be over here for some time. So.
Thank you, Professor Rامن. Please, if anyone has a question, just go ahead, ask him, or you can type, or you can say.
Dr. Ali, I have a question.
Yep.
Thank you, Professor Raamen, for this available lecture or workshop about this indentation. So my question is, what's the role of adhesion here in this indentation? We talk here about the indentation by atomic force microscopy. So the tip will be indent the matrix.
Yes.
There is very high forces will be found here, and so when the loading unloading forces here, this moving this slide, there is forces here, adhesion forces, and we need very high energy to dissociate this bond between the tip and the matrix.
Yes.
Taken into the account or not?
Yes, so that's a very good question, because a lot of the big difference between doing micro indentation or even diamond tip based nano indentation and AFM based indentation is that because here the tip is very sharp and the regions in which we are operating are very small, the role of adhesion can be very large. Now the amount of adhesion that you get between the silicon AFM tip and the polymer depends on the nature of the polymer. We are slightly lucky in the sense that because this is a highly cross-linked polymer, the indentation adhesion forces are small. In our current analysis, we are not taking into account the adhesion forces. And the reason why we know they are small is that we can actually measure these adhesion forces. So if you look at if you look at the indentation curve at 600 nanometers, we see that we load to about 850 nanometers. And when we unload it, we see negative loads about 30, 40 nanometers, so which is close to about 5% of the peak load. So the effect of adhesion will skew our results by about 5-10%, but the amount of adhesion remains the same irrespective of whether I am at 600 nanometers or if I go closer and closer to the interface. So in terms of getting the elastic modulus of the interface, our data is not that affected by adhesion. But if you were to apply the same technique to a softer polymer, such as an elastomer or a rubber or something like that, then yes, then you would have to account for adhesion in the models.
Yeah, maybe this right, but some people say this is very high forces and there will be effect on the modulus of elasticity in this scale.
Yes.
Okay, thank you for this answer. And there is another question here. You said there is some plastic deformation happened in the nanoscale. There is many people say there is no plastic deformation will happen in this scale. I mean nanoscale. So there is many papers published by Professor Fyodor Brodich and Emanuele Prosso say there is no plastic deformation will happen in this scale. Maybe some people say yes, other people say no, but I think there is no plastic deformation.
Yeah, so there are two ways to look at this. So the first question is, instead of plastic deformation, I think it's easier to say, do we have non-linearity in the loading process versus the unloading process? I think that's a better way to look at this, because instead of thinking of it as plastic deformation that you would get at a bulk region. So is there non-linearity in terms of loading and unloading? And the answer is yes, because for example, if you look at this loading and unloading curve, I mean, they are not both ending up at the same point. If this was, for example, if you were loading and unloading in pure silica, even with an AFM tip, then these two curves would completely overlap. So if these two curves completely overlap, that tells us that the deformation is primarily elastic. Here, what we know is that it is not primarily elastic. I mean, there is something other than elasticity, whether it is large-scale plasticity or it is other time-dependent behavior, or is it rheological behavior, or is it viscous behavior, we don't know. And honestly speaking, for our purposes, it doesn't matter because we are not looking at the loading curve. But you're right. I mean, you can carry out these indentation processes and you don't see any permanent deformation after the fact, right? But there is still some nonlinearity in the loading part, which does not exist when you unload it. And in terms of the analysis, almost all of our analysis regarding the elastic modulus is done, very early on in the unloading process, 10% down from the peak, with the idea that you're basically capturing the elastic unloading of the material, which is allowing you to get the elastic modulus. But I agree. Yeah, the classic definition of plasticity doesn't necessarily occur in this case.
Thank you very much.
Thank you, Professor. Is there any more questions, please?
Yep. This is Mushtaq speaking. May I ask a question, please?
Yeah, go ahead.
Thank you, Professor Stan, for your nice presentation and your times and efforts to giving us this nice presentation and having you at our University of Al-Qadisiyah. It's nice to see you again, D.Ali Fahad. I hope you remember me.
Yeah,
and
sure.
It's nice to see you again very well.
Sure.
Professor, my questions, actually, there are several questions. The most interesting questions, I'm currently working on development, on investigation, the mechanical behavior of composite laminates with different ply orientations and the effect of surface treatment, of fiber surface treatment on mechanical behavior.
Yes.
My question is, with the exposure of fiber for water vapor condensation or for UV, would that influence the fiber matrix interface, or would that change the weight of that composite? First question. The second question, with the effect of different ply orientation of fibers, would change with the AFM indentation on that? Thank you.
Okay, thank you. I think I can answer the second question easier than the first. So when you're talking about ply orientation and you're talking about effective properties of, using, let's say, classical laminate theory or something like that, the prediction of those properties is very different than what would go on at the fiber matrix interface. So there are two very different length scales. So even if something is going on at the fiber matrix interface, I don't think that will necessarily show up in the large scale structural, let's say, the bending behavior of a laminate. The fiber matrix interface properties do show up in terms of determining, primarily, for example, in terms of determine off-axis strength. So if you're looking at the tensile strength or a compressive strength perpendicular to the fibers, they also show up in compressive strength, even along the axis of the fiber, and they also show up in terms of fatigue, because fatigue accumulation in composites starts out with cracks in the matrix and cracks in the fiber matrix interface. So fiber matrix interface properties can play a lot of role in terms of fatigue accumulation. So the fiber matrix interface difference in properties ends up playing a role, but not necessarily in predicting the overall stiffness, but in terms of, let's say, predicting fatigue durability and so forth. So to answer your first question, will the presence of, for example, hygrothermal or moisture absorption, how does that play a role? We believe it will play a role. And the reason why we believe it will play a role is because physically the interface is different than the bulk matrix. That means chemically it has to be different. And if it is chemically different, then the response will be, if the cross-linking densities are higher, for example, then the response to UV, and not so much UV, water vapor is a bigger concern. The effect of water vapor will be very high. By the way, the reason why we study UV and not water vapor over here is because UV is easier to study. So if you take a composite laminate, and you look at the cross section, and you have the carbon fiber and you have the interface and you have the matrix, and you subject it to moisture absorption, we get moisture induced swelling. So when you get moisture induced swelling, the surface that was flat is no longer flat, and you can't polish it, because if you polish it, then you destroy the material that you're trying to look at. So studying moisture absorption using this technique is very difficult. UV was easier, but I think moisture absorption will play a bigger role in terms of changing the properties. So when you absorb moisture, the level of moisture uptake depends on the properties of the polymer. So if it is more cross-linked or less cross-linked, then the amount of plasticization you will get will be different. So if you're trying to predict the overall durability using measurements on bulk polymers, that may not translate well to a composite where the interface region is behaving differently than the bulk polymer. So I don't know, I gave a very long answer. I don't know if I answered your question or not. If I didn't, I'm more than welcome to I'm more than happy to clarify.
Dr. Mushtaq, I think you covered most of the question. So we still have time for one question. If anyone has something, please.
May I go ahead, or Dr. Ali?
Yeah, just go ahead.
Yes,
go
yes.
ahead.
Yeah.
Professor, you said about the swelling of the composite. Would that change the weight? Okay. Is that would that swelling would degrade? Would damage the fiber or the damage of the matrix after 1 hour of the UV exposure? And you said, because you showed us in one slide that there is a sinking of the load after 1 hour of UV exposure, and then it would increase after 6 hours. There is a little bit doubt about my information, because I believe when that damage after 1 hour, with the load transfer, just the fiber load, would the fiber just take the load? But there is no interface between fiber and matrix, because the matrix has damaged already after 1 hour.
No, so what we observe, if we go and look at the UV data, for example, what we are observing, and we can look at this, for example, the elastic modulus changing as a function of time, depending on where you're sitting. So if you're sitting 40 nanometers away from the carbon fiber interface, then you can see that the elastic modulus, let's say, decreases from 10 to about 5 GPa in the interface region, right? So, but this is only the surface phenomena. So in an actual composite, it's very difficult to study UV degradation, because UV degradation occurs only in the top 3 or 4 microns, and it takes very long hours of duration to observe anything. So for example, here we are looking at only 6 hours of duration, because the changes that are occurring in the material are only occurring in a very thin surface. But because we are using AFM based indentation, that is enough for us. So because we don't care about what is going on underneath. Okay. So to give you an example, when we first started out, these experiments were very long duration experiments. These are 1,000-hour experiments. So if you're dealing with a bulk composite laminate, then UV exposure, you have to carry out very long duration UV exposure before you start seeing changes in the material properties, right? Here we start seeing changes in the material properties very fast, because these indentation experiments are probing only the top 10, 20, 30 nanometers of the material, which almost immediately gets exposed. I mean, we start picking it up not only within 6 hours, we start picking up these changes within 30 minutes, because UV penetration in the top 1 micron is almost instantaneous, right? So you're starting to see change properties. But the fiber matrix interface is still intact. There is no physical damage to the fiber matrix interface. I mean, the fiber matrix interface still exists. If we look at, for example, AFM images of something that has not been exposed to anything and something that has been exposed to 6 hours of UV, we still see that the fiber matrix interface exists. But we start seeing maybe some oxidation of the carbon fiber, maybe some changes in the polymer matrix, but physically there is no damage that is occurring. I mean, we are very far from any physical damage occurring.
Thank you, Professor Raamen. Please, I think we are over now. If anyone has more questions, feel free to email Professor Raamen directly.
Yes.
His information and the brochure. Thank you everyone for joining us today. I think we're done.
Okay. Thank you.
رمضان كريم على الجميع، وإن شاء الله نشوفكم على خير.
Thank you, Professor Raamen, and thank you, Dr. Ali.
Thank you.
Thank you.
Ahmed, close it, please.
Okay.